Hello everyone, Deepak Pandey here, and this is the episode 2.3 of Breaking Gate 2020 in 45 days. Now in this episode as well, I am going to continue the topic of extraction. In the previous episode, I have discussed the type of components, the carrier liquid, the solvent and the solute, the type of mixtures that we have in extractions, where A and B are partially miscible, where A, B, B, C are partially miscible, and the third type where A and B are completely immiscible. I told you that in GATE examination, either you will be having that case where A and B are partially miscible, or you will be having that case where A and B are completely immiscible. I also explained then when you have to use mass ratio and when you have to use mass fraction. If you are using mass fraction, then what are the other things that you have to keep in mind? We also discussed the various configurations of extraction and the mass balances on them. Now in this case, in this episode, I am going to discuss the multi-stage extraction as well as the use of the triangular diagram and the use of the rectangular axis or the XY axis. So let us start. First of all, let us understand this triangular diagram, the basics of triangular diagram. So suppose this is an equilateral triangle, right? Suppose this one is an equilateral triangle. Let us name the vertices as A, B and C. Okay, these A, B and C are the same components that we have discussed in the case of extraction. So this one is carrier liquid, the solvent and the solute. Okay, now we should have the basic idea here that at this point you are having only A or 100% A, there is no B, no C. Similarly, at this vertex I have only B, and at this vertex I have only the solute C. So the vertices of this triangle denote respectively 100% C, 100% B. If you know these notations, then only you will be able to solve the problems on extraction, and 100% A, right? Now if you take any side you take, suppose you take the side AC and you consider a point here. Now a point on the side of the triangle represent binary mixture, means on the side of the triangle there are two components. But which two components? Because this point is present on the side AC, so this point should represent the component, a mixture of A and C, a binary mixture of A and C. Composition you can also find. Suppose there is another point, and let's suppose there is one more point. So I have divided this side into 4 equal parts. So if this is 100% A, this is 100% C. Let me make lines like this. You have divided each side AC and the side BC into 4 equal parts. Now let me write the composition of these 2 points. One thing you should understand, the very basic concept here. As you move away from a particular vertex, the composition of that vertex, the mass fraction of that vertex in the mixture decreases. Suppose, now because I have divided this line in 4 equal parts, then each point represents a change of 25%. Now suppose you are writing the composition of this vertex. So what should I write? This is 100% B. As you move away from here, now this point represents a mixture of B and C. But one step is a change of 25%. So you should have here 75% B and 25% C. Right? Similarly here, it is 50% B and 50% C. You can observe that I am using a change of 25% because I have divided the side into 4 parts. If you divide the side into 5 parts, then each step represents a change of 20%. If you divide the side into 10 parts, then each step is going to represent a change of 10%, right? Now this one should be 75%, okay, it should be 75% C and rest 25% B. So as you go away from the point B, the composition of B is going to decrease. Similarly, let's write the composition of all these points. So I hope you can write by your own, so try to write. And now this one is 75% A and 25%, what should I write here, B or C? Because it is present on the side AC, it should be 25% C. Similarly, 50% A and 50% C. So this is 25% A and 75% C, and then you have 100% C. Let us also divide the side AB. So I hope now you have understood how to solve these problems. Let us divide the side AB into 4 equal parts again. How to read the points on this triangular diagram, that is very, very important. Okay, then you can also join these sides like this. Now let me write the compositions of these points as well. So it should be away from B, so B should decrease, A should increase. Okay, this is also 25%, so this must be 75% B and 25% A. At this point, it should be 50% B and 50% A, and therefore at this point it must be 25% B and 75% A, and then you have 100% A. This is how you read a point on the side of this equilateral graph. So I hope now you know how to read the vertices, how to read the sides. Now what happens if there is a point inside the triangle? Suppose this point, and let's say one more point we take, let us say this point. How to read the composition at point, let us call it M, and let us call this point N. Fine. Now let me explain one more thing here. Then I'm going to write the composition of M and N. First of all, vertices represents pure components, sides represents binary mixture, and any point inside the triangle represents tertiary mixture. Means if you have any point inside the triangle, it should be a mixture of 3 components. All of the components A, B and C should be present. Now how to read this? So let me make a separate triangle here and explain another point. Suppose this is 100% C, and then you make a horizontal line like this. What is special about these lines? Suppose I have a gap of 25%, still a gap of 25%. So it means that if I ask you that what is the composition of C here, you'll say that it is 75% C and 25% B, and this one is 75% C and 25% A. But A and B are changing definitely. If you go from this point to this point, A and B are changing. But what can be said about C? You must say that along this line, C is constant, and that is 75%. Similarly, this is a line representing 50% C. This is a line representing 25% C, and this is the line representing 0 C. Suppose you make lines parallel to opposite to the vertex B and parallel to this side, of course. Now how to understand these lines? This line represents, this is 100% B, so this line represents 75% B. This line represents, along this line everywhere at any point you must have 50% B, and this line represents 25% B, and this is 0 B obviously. Similarly, if you join these vertices, then what you are going to get? Suppose I am joining this. These lines are not exactly parallel, don't worry about that. Now suppose I am joining these lines, right? Now this is 100% A, this line represents 75% A, everywhere A is 75%. The other component composition is of course changing, right? This is 50% A and this one is 25% A. This line is 25% A. So what we observe, if you draw a line opposite to a particular vertex, it shows the constant composition of that particular vertex. Fine. So if this is vertex C, you are drawing a line here, it means that it is constant C line. What is the composition? At 75%. If you are drawing this line, it must mean that it is constant C line at 50% C, constant C line at 25% C. Suppose you take vertex B, so 75B, 50B, 25B, 0B, and so on. Similarly, you can also read here. So how to read it? Suppose I am writing the composition of point M. Now try to read by your own. Point M is the intersection of this line, and this line. Now for this line, it represents composition of A. And what composition? This is 75% A along this line. This is 50% A. So it means that at the point M also, A must be 50%. Clear? Now let us talk about B. This is 100% B, 75B, 50B, and what is this? 25% B. So it must be 25% B. Now you can directly write that C is 25%, or let us check also 75C, 50C, 25C. So 25% C. That is the composition of point M. Similarly, point N. So try to write first the composition of point N on your own. You can pause the video. Now, see the point of intersection. This point is made up of these three lines. The point of intersection N is made up by these three lines. Okay. Now, this line. Okay, let us talk about A. So this is 100A, 75A, 50A, 25% A. So it must be 25% A. Let's see the B composition here at point N. We have here 75B, 50B, 25B. So it must be 25% B. And what about C? 75, 50, 50C. This is how you read a point which is present inside the equilateral triangle. So first of all, if you want to understand the concepts, if you want to solve the numerical problem based on triangular diagram, you must understand these basics. Now based on this, also you will find one or two questions in GATE examination where you have to directly read the values from the triangular diagram. Fine. Just go through whatever I have discussed here. Now I'm again going to explain you some concepts related to the triangular diagram, and then we'll go into the detail of these calculations of extraction problem, right? So if you have gone through the previous lecture, I told you that there is one type of mixture where A and B are partially miscible. So the raffinate as well as extract, both of them are going to contain all the three components, right? Now for these kind of mixtures, the equilibrium diagram is given as this. This is the equilateral triangle. The vertices are shown like this. This is the equilateral triangle diagram. Okay, no need to worry about that from where this diagram came, because equilibrium diagram is always obtained by the experiments. Now you are not going to do the experiments, so just remember that how the equilibrium curve looks like. Now this black curve is sometimes called as binodal curve, or sometimes called as binodal curve, or sometimes it is simply called as the equilibrium curve, right? It is also known as binodal because it has two nodes, this node and this node. So binodal curve. Fine. Now what is so special about this curve? First of all, you must understand that the region outside this curve, this region which is outside the curve, is called homogeneous region. Fine. While the region which is present inside this curve is called heterogeneous region. Now, what is the meaning of this homogeneous and heterogeneous region? Fine. I'm going to give you a very basic and very important concept here. Please learn it carefully and please try to understand it. Suppose there is feed. I told you that what is feed? Feed is a mixture which contains the carrier and the solute. Okay. So the feed contains carrier as well as solute. So suppose we have a mixture of A and C, right? In this mixture of A and C, you are adding some amount of solvent B. Now, can you tell me that where this mixture of A and C lies on this diagram? Obviously, the binary mixture always lies on the side AC because it is a mixture of A and C. Suppose the binary mixture lies here and let us call this as F. So, F denotes the composition, this dot denote the composition of the mixture of A and C. Fine. Now, suppose in this mixture, you are adding solvent B. So, where is solvent B? I am assuming that this is pure B. So, where is pure B in this triangular diagram? This is pure B. Now, I am going to give you a very important concept. The concept says, if you are adding B to a mixture of A and C mixture denoted by this point, B component denoted by this point. Now, when you add these two, you will be getting a ternary mixture. And a tertiary mixture, you will be having three components there. Now, where is that point which denotes the composition of that mixed stream or mixture formed? Now, that is always given by, or that always lies on the line joining the points F and the points B. I'm again repeating the concept. When you mix feed and solvent, then the composition of the mixture always lies on the line joining the F point and the B point. Somewhere, it may be here, it may be here, maybe here, anywhere, but always on this line. This is called the mixing rule. Suppose I gave you the diagram in the previous lectures that this is the mixer, and in this mixture, what is entering? Feed is entering, and what is entering? Solvent is entering. Suppose solvent is pure B, it may contain some C, that is not a problem. And what is there in the feed? It has A plus C. Fine. So when you mix them, definitely you are going to get a mixed stream. The mixed stream flow rate is M and the composition is XM. Right? So where is this mixed stream on this triangular diagram? So the concept says if these two are mixed, join the 2 points. Now the mixed stream always lies on this point. Where is the point M? It depends upon how much quantity of solvent is added. As I told you that the composition is more closer to that point which is present in excess. Now suppose in this case or in this mixture of A plus C, you are adding a very small amount of B. So majority of the feed is there. So the mixed feed composition is going to lie here. Right? Now suppose you added small amount of B and then you leave it for some time. What do you think? Extraction will occur or not? Definitely not, because this region lies in homogeneous, and homogeneous means single phase. And what is desirable in case of extraction, homogeneous or heterogeneous? You must think about this. In case of extraction, the desirable thing is the phases, the mixture that you have created, this mixture, when you leave it, this mixture must be separated into two phases, raffinate and extract. And if this is not happening, then extraction is not happening. So for extraction to occur, the mixture must separate into two phases, raffinate and extract. And when the mixture is going to separate into these two phases, the separation will take place if the mixture lies in the heterogeneous region. That is the meaning why I am calling this region as heterogeneous. Now when the mixture is going to lie in the heterogeneous region, suppose you are adding some amount of B and then you did the material balance calculation, your composition lies somewhere here. So it is homogeneous region, extraction is not going to occur. You add some more amount of B, you will shift here. And slowly as you add more and more amount of B, suppose you added such amount of B that the final composition, the point M, reaches here. Now what do you think? Extraction will occur or not? If you leave this mixture, after some time you will find that there are two phases separated and definitely extraction has occurred. Getting my point? Now if you leave them for settling, this is the settler, then definitely there will be two phases, R phase and E phase. I gave you the details of these two. Now where are those R and E phases? In this triangular diagram, so in this triangular diagram, there are some lines. Now these lines you cannot draw on your own. These lines must be drawn by experiments. These lines are called tie lines. And unlike distillation, these lines are not parallel. In fact, in most of the cases, these lines try to, they are moving in a particular direction. These lines are moving in this particular direction. So most of the case, this happens, most of the cases. Now, when your point M, suppose your point M was initially here. Suppose when you added very small amount of B, your point M was here. So extraction was not occurring. When you added some more amount of B, point M shifted here. Again, extraction was not occurring. But when you add sufficient amount of B such that the point M lies anywhere in this region. Please remember that point M is always going to lie on this line, but can be anywhere along this line depending upon the amount of B you add. So you added sufficient amount of B such that your point lies here. Then you leave the mixture. What is going to happen? There is a line, there is an equilibrium line, tie line passing through this point M. Fine. Now after some time you will find that the mixture has separated into two phases. One phase composition is given by this dot and other phase composition is given by this dot. You must know what is the role, what is the use of tie line. The end points of the tie line gives the composition of two phases in any operation. This is true in case of mass transfer as well. So what is this? This is the composition of raffinate or extract. This is the composition of raffinate or extract. You can see that this point is more closer to A. Means at this point A is more. And the phase which is rich in A is called raffinate. The phase which is rich in B, it's called extract. So this composition is extract composition. This composition is raffinate composition. This is how you have to understand the triangular diagram, the equilibrium diagram. Now one more point here. Suppose you are saying, I am saying that if you are not adding sufficient amount of solvent, extraction will not occur. But suppose if you add very high amount of solvent, what is going to happen? The point M, if you keep on adding solvent, the point M is going to shift here. And it is also possible if you add very high amount of solvent, the point M may shift here. What do you think? Extraction will occur or not? Again, no extraction should occur because this region also lies in the homogeneous region. Fine. This is how you have to understand the triangular diagram, right? Okay. Now, this triangular diagram is used in those problems where A and B are partially miscible. If A and B are partially miscible, then only you are using the triangular diagram. If they are not partially miscible, means what is the other case? A and B completely immiscible. In that case, triangular diagram is not required. In that case, we can use the x-y coordinates. So I am going to explain that one also. Suppose A, B are immiscible. So when A, B are immiscible, definitely each phase, raffinate as well as extract, is going to contain only two components. Raffinate contains A and C and extract contains B and C. Now in this case, I can define, first of all, you should understand in this case, I can define composition X and composition Y. So what is composition Y? It is mass of C by mass of B, and X is mass of C by mass of A. Fine. These are called solute-free concentrations. And in this case, triangular diagram is not used. In fact, your calculations becomes more simple and we use Y-X diagram. You can call it rectangular axis. You can call it capital XY axis. You can call it solute-free axis. It's up to you. I have explained what is the meaning of solute-free concentrations. Now in this case, the equilibrium curve is something like this. This is your equilibrium curve. it may be some relation between y is equal to phi x. Now, as far as gate exam is concerned, this equilibrium curve is going to be linear. Okay, so y is equal to mx kind of relation will be there. But you have to, no need to worry about the equilibrium curve, even either in this case or in that case, because equilibrium curve is always provided to you. You are not there to find the equilibrium curve. You can only find the operating curve, not the equilibrium curve. So this is the equilibrium curve. Fine. Now this will be given to you. Also, the operating line, when suppose we are having yx line and the equilibrium curve is given to you. Now what is the operating line? So I'll come to the operating line before when we will discuss the multiple stages or the single stages in that case. But what I want to make here clear is, if A and B are partially miscible, we have to use the triangular diagram for calculation of number of stages and other calculations as well. And if A and B are immiscible, then we are going to use solute free axis and these coordinate solute free diagrams. Okay. So now after discussing this, let us also discuss the operating lines in this case. So now multi-stage cross current extraction, and I'm assuming that A and B are immiscible. So as I explained, now you should not think, you should not be worried that why I'm not using the triangular diagram here, because A and B are immiscible, so triangular diagram will not be used. So just make a simple rule. If A and B are partially miscible, then you have to use the triangular diagram to calculate the number of stages. But if A and B are immiscible, completely immiscible, in that case, I will use the capital X, capital Y coordinates. Okay, so let me make the stages first. And I'm going to explain everything by using the 2 stages only. There can be 3 stages as well. As far as gate exam is concerned, the numerical problems will be asked based on 2 stages only, not based on 3 stages. Otherwise, the calculations will become complex. Now, this is called the multi-stage cross current extraction, and I have assumed 2 stages here. Okay. Suppose this is the total feed and the mass fraction XF, and this one RS is the flow rate of only A, the solute free flow rate. I have discussed how to find RS. RS is given as F into 1 minus XF. And suppose the mass ratio is XF, you can also call it X naught. Now this is the refinite R1, mass fraction X1, solute free flow rate RS, and mass ratio X1. Refinite R2, mass fraction X2, solute free flow rate RS, and X2. In cross current extraction, even if not provided in gate examination, you have to consider that the solvent flow rate in these two is same, as well as the mass fraction in these two is also same. So it is by default, but yes, if it is provided in the question that these two are different, then definitely you have to agree with the question, the data given in the question. But if not provided and still it is required for solving the problem, always you can take these two as the same flow rate and the same composition. Also, suppose ES is the flow rate of only B, the solute free flow rate, and capital YS is the mass ratio of the solute. So this is also ES, and YS, let us call this as E1, Y1. I'm writing these things in pair. You should always remember which two you can multiply and which two you cannot multiply. ES capital Y1, and this one is E2, Y2, and ES capital Y2. Fine. Now this is the problem. Now I will analyze this problem on the solute free coordinates, not on the triangular diagram. First of all, do you know that what is the equation of operating line for cross current extraction? First thing you should understand, for extraction the operating line lies below the equilibrium line, right? That can be easily proved. I'm not going to discuss that here in detail. The second thing is either whether it is multi-stage or single stage. If it is cross current, then the operating line equation remains same. So don't think that if it is multi-stage, then the operating line equation is going to change. The equation is not going to change. So first of all, what is the equation for multi-stage, this cross current extraction? Let me draw here the graphs. The equilibrium curve, capital Y, capital X, What is y? C by b. What is x? C by a. Now the operating line for cross current is, okay, suppose even if you don't know how the operating line looks like, but at least you should know it lies below the equilibrium curve. Can you tell me that what is the highest value of x here and what is the lowest value of x here? Definitely in the feed, the amount of solute is highest. So xf must be highest and x1 and then x2 must be lowest. So if you want to start plotting the curve, this is your xf, suppose. Fine. And definitely x2 is lowest, xf is highest. Now, which two compositions are related by operating line? Now I'm giving you a concept. Please, you should remember it everywhere in all the mass transfer operations. The compositions of those streams which are leaving from a particular stage is related by equilibrium line. The compositions of those streams which are present on the same side of a stage is related by operating line. Getting my point? The leaving stream composition is related by equilibrium line or the equation of the equilibrium curve, and the compositions of the stream present on the same side is related by the operating curve. So these two must be related by the operating curve. These two are leaving, right? So leaving must be related by equilibrium. Fine. These two operating. Getting my point? These two equilibrium. So leaving streams must be present on the equilibrium. Same side streams must be present on the operating. So again I am telling you, these two must lie on the operating, these two equilibrium, these two operating, these two equilibrium. So along with xf, which one is present at the operating line? Ys. Now definitely which one is smaller, ys or y1? What do you think? Ys or y1? Which one is smaller? Solute is getting transferred from feed to the solvent, so y1 must be more than ys. So ys is somewhere here, suppose. If ys is 0, then definitely ys is here. Now you make a dotted line. So what is this point? This point is xf comma ys. Right? Now you must know that for a cross current extraction, the slope of operating line, you must have learned this in your course, that the slope of operating line is minus rs by es for cross current extraction. So if this point is xf comma ys, you make a line having slope minus rs by es. And the point where it touches the equilibrium curve, fine, this is the equilibrium curve. So can you guess which point is this and which point is this? Now this point lies on the equilibrium. It must be x1 and y1. So this one is y1 and this one is x1. Fine. Now these two, x1 and ys, they must be related by the operating line. So the next operating line must start from here. This is x1 and ys. What is the slope of this? What can you say about the rs? This rs and this rs, they won't change. And I'm using the same solvent flow rate. So es is also same. So minus rs by es remains same. And therefore, you should make a parallel line. Again having a slope of minus rs by es. So what should be the coordinate of this point? Again it lies on the equilibrium. Fine. So this point must be y2 and x2. So that is x2 and that is y2. Right? That is the solute free axis diagram of this process. Now you can verify. Let me verify few things, clarify few things. xf is highest, right? Then x1 is less than xf and then x2 is less than x1. ys is same, y1 is more than ys, y2 is more than ys. But what is the relation between y1 and y2? That you can see clearly here. Fine. Now numerical problems are asked in this kind of case. For that particular case, the equilibrium curve is also given as a linear one. Now we can also define few things here. One thing is called percent extraction. Percent extraction. What is the meaning of percent extraction? It is the ratio, means how much solute has been extracted divided by how much was present initially multiplied by 100. So how much has been extracted? You can say that the solute extracted is equal to what was the solute present initially. Let me first write solute present initially. Can you multiply these two, rs into xf? Yes or no? Definitely yes. This is solute free flow rate, this is solute free concentration. That is the initial solute present. What is the solute removed? So what is removed? Removed means initial minus final. So that is Rs multiplied by Xf minus X2. That is the solute removed, and if you multiply this by 100, then definitely you are going to get, let me write this as 1 minus X2 by Xf into 100. This is called percent extraction. Sometimes it is asked in the question or sometimes it is given in the problem. Now let me clarify one more thing. Many students, when this kind of question comes in the examination, many students, what they think that the amount of solute removed in this stage and the amount of solute removed in this stage are same. But this is not so, and it is very clear from the graph. You can see here that in the first stage, you are present here and the equilibrium is here, and this gap denotes the driving force. So in the first stage, the driving force is very high, and definitely in the first stage, more amount of solute is removed, right? And in the consecutive stages, comparatively less amount of solute is removed. What is the amount of solute removed in the first stage? That you can write as Rs into Xf minus X1 or Es into Y1 minus Ys. Fine. What is the solute removed in the second stage? Let me write also the solute removed in the first stage. Solute removed in the first stage. And that is equal to Rs multiplied by, please note that whenever I am using Rs, I am always using the capital letters concentration, the mass ratios, Xf minus X1, or it is also equal to Es into Y1 minus Ys. While solute removed in the second stage is definitely not same as before. You should never say that these two stages are going to remove the same amount of solute. Of course, because the driving forces are different for the two stages, so amount of mass transfer is also different, right? So for the second stage, you can write that the solute removed is Rs is always remaining same, X1 minus X2, or Es into Y2 minus Ys. Now you can easily see in this graph which one is less, Y1 or Y2. Y2 is less, so Y2 minus Ys will be less than Y1 minus Ys, and definitely therefore more amount of solute is removed in the first stage and less amount of solute is removed in the second stage. That is one thing that most of the students make mistake. The other things are sometimes what they do, that they multiply this R1 and this ratio. That is not correct method. I always told you that either you multiply this or you multiply this. Many students always ask me, sir, what should be used while doing the calculations, ratio or fraction? So when you do the calculation, always check the equilibrium relation. Fine. So equilibrium relation is most of the time in case of extraction, it is given in ratios. So always ratios are used. And when A and B are immiscible, we always go for ratios. And of course, one more point I would like to clarify here. If you want to solve a numerical problem, you have to assume that A and B are immiscible. Otherwise, you cannot solve a particular problem. Fine. So this is the concept of multi-stage cross-current extraction. Now I'm going to take few problems from GATE so that whatever I have discussed till now, let me clarify those things, and there are some doubts as well. The students are asking those doubts. So the doubts will also be clarified. Okay. Now students, this one is multi-stage counter-current extraction when A and B are partially miscible. Please note that I'm writing here partially miscible. So whenever I'm saying that they are miscible, I cannot go for mass ratios, right? And I cannot use the solute-free coordinates, the XY coordinate. What I have to use? Here, there is no other method. I have to go for the triangular diagram for the calculation of stages. So let me explain that how you have to understand the multi-stage counter-current extraction and the triangular diagram for this particular case. Suppose we have three stages here. So for the sake of simplicity, I'm taking three stages. Actually, the stages are not known before. We have to find the stages. But here, for the purpose of explaining the concept, I'm already assuming that I'm having three stages. So this is multi-stage counter current extraction. Now please note, I'm not going to use here RS and capital X, right? Mass ratios won't be used. So this is F, XF, R1, X1, R2, X2, R3, X3. This is, you can call this as the solvent S, and composition Y0 can be YS as well. This is E3, right? And Y3, because it is coming out from the stage 3, so I should write as Y3. This is E2, Y2 and E1, Y1. Okay. Now, if you can understand that we can use the concept of total mass balance for the entire stage here. Fine. So, can you write this as F plus S is equal to R3 plus E1. Fine. Definitely, the total things which are entering and the total which is leaving, they are in equilibrium. The total which is entering and the total which is leaving, they must be same. Fine. Now, many students, they ask this thing that, sir, is this stream and this stream, are they in equilibrium? No, definitely not. They are not in equilibrium. Fine. So if this confusion you have, please clarify here. These two are not in equilibrium. However, these two are in equilibrium. These two are in equilibrium. These two are in equilibrium. Fine. These two present on the same side. Operating line, operating line, operating line, operating line. So streams present on the same side, operating line, stream leaving from a particular stage, equilibrium line. Getting my point? Now F plus S is equal to R3 plus E1. Can you also write this as F minus E1 is equal to R3 minus S, and let me write this as delta. Delta is just a symbol, do not worry about this, and let me call this equation as 0.1. Fine. Now also we will write the balance on the first stage, on the second stage and on the third stage individually. So for the first stage, what is the balance? The first stage balance says F plus E2 is equal to R1 plus E1, and this can be written as F minus E1. F minus E1 is equal to R1 minus E2. If you see this equation, F minus E1 is also equal to this, and delta F minus E1 is also equal to this. So this must be equal to delta, equation 2. Now let me write the same balance for stage 2, which shows R1 plus E3 is equal to R2 plus E2. Okay, and this can be written as R1 minus E2 is equal to R2 minus E3, because R1 minus E2 is equal to delta and R1 minus E2 is equal to R2 minus E3. This must be equal to delta, and let us call this as equation 3, and so on. You can also write various equations for various individual stages. So why I am writing these two? Let me also tell you the concept of mixing. When I am writing A plus B giving C, material balance, or F plus S, let me write as F plus S. A, B, C, we are using 4 components. When I am writing F plus S is equal to M, what I told you, that the point F and you connect point S, and the point M must lie somewhere here. This is one rule. But if you write, suppose, let me take as this equation, R minus E is equal to anything, suppose delta, right, random equation. If you write this, how to understand this equation? It says that if you join the point R and the point E, R and E, the delta point must lie on this line. Here also, M point must lie on this line, delta point must lie on this line. But what is the difference between these two? The M point lies in between F and S, while the delta point lies if you extend this line. So either the delta point will lie here or it lies here. So can you guess where the delta point lies? Right, the delta point must lie here, right? So I'm leaving this to you, why delta is lying here, why not there. This is very easy concept, you can easily understand, right? So this concept will be used, this particular concept will be used for analyzing these equations. F minus E1 is equal to delta, right? R3 minus S is equal to delta, R1 minus E2 is equal to delta, and so on. So I'm explaining how to locate this equation, how to show these equations on the triangular diagram in the case of multi-stage counter current extraction. This is the diagram given to you. Fine. Now one by one follow each equation, right? First equation has 4 terms, F, E1, R3 and S. Let me locate these 4 terms. So where should be F? Definitely F should be somewhere here. Fine. Where is E1? E1 is the composition of extract. Extract composition always lies on the equilibrium curve. I'm assuming A and B partially miscible. It means extract contains all the 3 components, should lie inside the triangle, and because it is extract, it should be closer to B. So suppose somewhere here, this is the extract composition. So this must be E1. Do not make E1 at this side. E1 must lie on the equilibrium curve. Fine. Now this is R3, raffinate. You can also see that raffinate is that stream which is rich in A. Now R3 is this stream. And R3 must contain least amount of solute because the solute has been transferred, right? 3 stages have been used. Now the very less amount of solute is present here. And raffinate R3 must lie on this arm. This is called raffinate arm. This is called extract arm. So R3 must be somewhere here. Very less amount of, very less amount of C. So let us call this as R3. And where is S? S is the solvent. Now depending upon you are using pure solvent or not. If you are not using pure solvent, then S must lie somewhere here. Let me take pure solvent. So my point S is this. So S and B, they are same. Fine. Now, if you see that concept and the equation, which 2 lines we have to join? F minus E1 is equal to delta. It means that if you join F and E1 and you extend it, then delta must lie somewhere on this line. Getting my point? So no need to, no need to mug up everything. Just understand how to write this equation. Once you write this equation, you will automatically come to know that which 2 points you have to join and where is delta. Now it also says R3 minus S. So which 2 points you have to join? R3 and S. So join these 2. Fine. Extend it. And it says that delta also lies on this line. If a point lies on 2 lines, it means that the point is the point of intersection. So what is this? Delta. So I hope it is very clear how I made these lines and why I'm joining only F and E1 and only R3 and S. I'm not joining any other points. Totally depends upon the equation. Now I have made complete use of the first equation. Go for the second equation. What it says? F minus E1 I have already used. R1 minus E2. Okay, let me make one more point here. This is extract composition, and please do not think that this is the tie line. This is not the tie line. This is extract composition, and definitely there must be a tie line from here. You are not going to draw the tie line. Tie lines are already there. So what is this point? This point must be R1. Fine. Now the question says R1 minus E2 is equal to delta. It means that if you join R1 and E2 and extend it, it should pass through delta. But I don't have E2, but I have delta. So what I should do? I should combine delta and R1 and extend on the right hand side. I hope you are getting my point. If you combine these 2 and extend on the right hand side, what should be this point? I guess all of you understand this must be E2. Now there must be a tie line passing through E2. So draw a tie line passing through E2. And what is this point? This is R2. Fine. See the other equation. R2 minus E3 is equal to delta. It means if you join R2 and E3 and extend on the back side, it should pass through delta. So if I join delta and R2 and extend on the right hand side, it should pass through E3. Fine. There must be a line, tie line passing through E3, and it must go through R3 definitely. Then what you do? You can, this process, actually what happens, initially we don't know the number of stages. We know these compositions only, and the number of stages has to be calculated. So this procedure continues till you reach the final composition, and then what you can do, you can count these lines, the green one or even the blue ones, these ones. You can count these lines. Let us count these green ones, the tie lines, and then you can say that this much number of stages is required. This is called the graphical method. Now in GATE examination, nobody is asking you to draw this graph and count the number of stages, but definitely the understanding is required. how to locate a particular point on this triangular diagram is very, very important. And there are some questions, if you have gone through the previous year problems, there are some questions on this kind of triangular diagram as well. So I hope this portion is also very much clear to you. Now only this much I will discuss in the theory part of extraction. Now let me directly come to the questions so that you will be more comfortable with the topic, that how to use the formulas. Okay. Hello students, this problem I am taking from year 2018. So here there are two extractors. So it is a double stage cross current extraction, right? The feed contains 20% A and 80% B. Now the usual notation is slightly different. Here A is the solute, B is carrier, and C is solvent, right? It is given in the problem that the solvent is pure. Solvent is pure and same amount of solvent is used in both the stages. As I told you in the discussion in the theory part, that in multi-stage cross current, if nothing is mentioned, then by default what we assume that both the stages same amount of solvent is going and same concentration of solvent is entering, right? So solvent is pure and same amount is used, right? What else is given is the equilibrium relation, which is y star is equal to 1.5x. Now y star is equal to mole of solute, which is A, divided by mole of solvent, which is C, and x is equal to, so 1.5 times, x is equal to mole of solute by mole of carrier, which is B. Fine. Now this problem clearly says that the equilibrium relation is given in terms of mole. Fine. So no need to convert it into mass. As I told you that most of the extraction problems are solved on the basis of fraction mass compositions, either mass fractions or mass ratios. But in this problem, the equilibrium relation is given in terms of mole. It means that the entire problem will be solved in terms of mole. That is the first confusion most of the students get in this particular problem. Now also, it is a ratio, it's not a fraction, it's a ratio, the equilibrium relation. This is very, very important because this is going to tell you that how to solve the problem in terms of ratios or in terms of fractions, in terms of mole or in terms of mass. So this problem will be solved in terms of mole, that is the first point, and second point in terms of ratios. It is also given that B and C are immiscible, means carrier and solvent, they are not miscible with each other. What does it mean? It means that the entire, each and every stream will be having only two components. The raffinate will be having solute A and carrier B, and the extract will be having solute A and the solvent C. So I am going to use, no need to use the triangular diagram for this problem. I explained that triangular diagram is used in case A and in case the carrier and the solvent are partially miscible. Also it is given that 60% of A entering in the feed is extracted in stage 1. In stage 1. Now what is being asked? That mole fraction, not fraction, they are saying mole percentage simply. This was written in the problem, that what is the mole percent of solute in the raffinate coming out of stage 2, right? So this is the scenario which is given here. Now the questions is asking you mole percent in R2. Now as I told you in the previous lectures, in the lectures of drying also, whenever question says, suppose that the moisture content is 50%, so you have to assume by default, if nothing is mentioned, that the 50% is solute by solution, not solute by solvent. Similarly, what is this mole percent? Now most of the students in this particular year 2018, they got confused. They said that everything is given in terms of ratio, right? So this is also ratio multiplied by 100. No, by default, if nothing is mentioned, mole percentage is always fraction multiplied by 100. Means what is this? Solute by the entire solution multiplied by 100. That you have to report. So most of the students, what they did, they found the value of this capital X2 and then multiplied this capital X2 by 100. Now that was a mistake. This mole fraction or mole percentage is not equal to X2 multiplied by 100, but it is equal to small x2 multiplied by 100, right? So suppose you want to find this. So first of all, you have to find the amount of solute and then the total solvent here, total solution there, and then multiply it by 100. So first of all, the information is given about stage 1. That 60% extraction is occurring here. So first of all, use that particular information and then find something. Then that something will be used in the second stage. So suppose basis is 100 mole. So I can write that XF is equal to 20 by 80, which makes it 1 by 4. What is Y naught? Pure solvent, so it is 0. Let us call this as, suppose ES is entering. Now ES is equal to S. Why? Because the solvent is pure, right? So ES is leaving, and suppose this is Y1. This is R1. And what is the value of RS? RS is the flow rate of carrier only. So what is RS? RS is 80. And let us say that this composition is X1. Fine. So let me first write the balance on stage 1, which says for stage 1, X1 is equal to, because see, 60% of the solute present initially is removed. 60% extraction has occurred, right? What does it mean? It means that the amount of solute present here is only the 40% of the initial solute. So I can say that X1 is equal to 0.4, 40% of initial solute present, and therefore 80 is not going to change. So what is capital X1? 0.4 into 20 by 80. That I can directly write. Why? Because this 80 has not changed and 60% of solute has been removed. So only A is going to change. So directly you can write X1 is equal to this. Fine. Now, if you use the equilibrium relation, it says that Y1 is equal to 1.5 times X1, which is, this is 1 by 4 and that is 0.1. That is equal to 0.15. Fine. Now if we write the material balance for the stage 1, we can calculate that what is the amount of solvent that was used in the stage 1. So this gives you 80 into XF, which is 1 by 4. Please note that this is solid free flow rate, this is solid free concentration, so no problem. Plus, there is no solute entering here, so that is ES multiplied by 0 is equal to ES multiplied by Y1 and plus 80 multiplied by X1, and X1 was equal to 0.1. Fine. From here you can calculate the value of ES. Y1 is 0.15, so that can be substituted. This becomes equal to 80 is equal to ES into 0.15 plus 8, and therefore ES is equal to 20 minus 8 divided by 0.15. Fine. This gives you ES is equal to 80. So the same ES will be used in the second extractor, second stage as well. Okay, so for the second stage, let me write the component balance equation, which is 80 multiplied by X1. What was X1? We already wrote, that is 0.1 plus what is entering from the top? 0. So let me write directly equal to 0. is equal to what is leaving from here, that is ES multiplied by, let us write this as capital Y2. So ES multiplied by capital Y2, we already found ES, so let me write here 80 multiplied by capital Y2 plus RS, which was 80. What was RS? Okay, RS was also 80, fine. So RS, which is 80 multiplied by X2. So two unknowns are present. Obviously, you cannot use a single equation to find two unknowns. What is the other equation? These two must be in equilibrium. Why in equilibrium? Because they are leading strings. Right? So Y2 is equal to 1.5 times X2. We substitute the value of Y2 here. It becomes 80 into 0.1 becomes 8 is equal to 80 multiplied by 1.5 multiplied by X2 plus 80X2. Fine. From here, you find the value of capital X2. Now, please note that capital X2 is not the final answer. First of all, calculate capital X2. You will be getting capital X2 is equal to 0.04. But please note that it is the ratio, and I told you by default, mole percent means fraction multiplied by 100. So, what is small x2? Capital X2 by 1 plus capital X2, which is going to give you 0.384 approximately. The values may vary a little bit. So, what is percentage? Now, many students, they did the problem up to this point correct, but they forgot to convert it into percentage. So, what is the final value? 3.84%. Right? So, I hope the explanation is clear to you. Right? There should be no confusion. You should not say that there is 60% extraction here, so there will be 60% extraction here. As I explained in the graph, that more extraction takes place in the first stage and less extraction takes place in the second stage. Okay? So, that was the explanation for this problem. Let us discuss another problem from GATE 2015. Now, this problem is based on partial miscible carrier and solvent, right? So, definitely when they are partially miscible, triangular diagram will be used. But this is not a numerical problem, this is just based on the understanding of the triangular diagram. So, the next problem is from 2015 GATE. If you read the problem carefully, what is given here? There is a feed which contains carrier A and solute C. Now, in this problem, normal standard notations are used. So, you have to read the problem that which one is solute, which one is carrier. So, always read the problem, do not assume anything, right? And solvent is B, right? So, as we have discussed in the lecture, same notations are used. So, in the extraction, it is being used, and in this problem, they are miscible. Even if it is not mentioned, they are miscible. They are using triangular diagram, it means that they are miscible, right? Triangular diagram is only used if the solute, sorry, not the solute, the carrier and the solvent, they are partially miscible. Now, from the extractor, raffinate is coming out. This raffinate contains what? This raffinate contains all the three components A, B and C in some proportions. Now, this raffinate is sent to a distillation column. D stands for distillation, E stands for extractor. This raffinate is sent to a distillation column from where this is pure B, fine, and this is P, which is a mixture of A and C. So, the distillation column recovers a mixture of A and C and separates B. Now, that B can be again used as a solvent in the extraction process. This is what usually happens in industries. After extraction, extraction is always followed by distillation. Now, what the question says? The question says that this composition is shown by which point in the triangular diagram. Now, that's why I told you that the understanding is important. You cannot make the tie lines, you cannot just locate the points, you cannot simply read the points from the triangular diagram, but the understanding, right, the coordinates are very, very important here, and a theoretical question can be made to confuse the students. Fine. So, where is this point R located? So, what are the options? The options are V, U, E, right? There was one more point, I guess the point is missing. The point was somewhere, it was T, something like that. Okay. Now, let us verify few things. The solvent is pure. So, where is this pure B located? Of course, this point. This is pure solvent. The point P contains binary mixture of A and C, right? And binary mixture are always located on the sides of the triangle. So, A and C, which is P is made up of mixture of A and C. So, where is point P? It is directly written on the diagram. So, this is the point P, which is a mixture of A and C. Fine. Now, the question says, where is the raffinate? if you read this problem for the first time, definitely you are going to feel this is going to be a very, very difficult problem because it's quite lengthy, contains two diagrams and a lot of notations, lot of symbols and all, right? But this is the easiest problem in GATE 2015. As I told you that if you combine F plus S and you are getting M, then what is the rule? That M must lie on the line segment joining F and S. Now this is raffinate. When you are distillating the raffinate, what you are getting? P and B. In the reverse manner, you can say that if you join P and B, what you should get? You should get the raffinate. Getting a point? If P plus B is giving R, what does it mean in the triangle diagram? That R must lie, the raffinate must lie on the line joining P and B. Now this is the easiest method you are not going to find in any book. That if you join P and B, raffinate must lie on that line. Now where is the line PB? You can identify yourself. PB. So this is the line. Fine. So either this should be the raffinate or this should be the raffinate. Now definitely you know that this is the extract arm. So raffinate cannot lie here. So where is the raffinate? Raffinate must lie here, and therefore U is the final answer. See how easy problem. Even I am taking this much time because I have to explain you. This problem should be done within 30 seconds or 45 seconds. If you have understood the concept and if you have read the problem carefully. But for the first time, if you read the problem and just leave it because it's quite lengthy, it's quite big to see the problem, then definitely you will not be able to solve the problem. So that was the second problem of extraction. So I hope the concepts was clear. This was these two particular problems most of the students were requesting to solve. Other problems as well you can solve in extraction. There